Since its early beginnings, Earth has been under a constant bombardment by objects from our solar system. Generally, this bombardment doesn't affect our lives very much, because our planet's atmosphere is thick enough that very few of these objects ever actually reach the ground. Most of them burn up in brief flashes that we can see in the night sky as shooting stars. Occasionally, though, Earth crosses paths with objects that are large enough to penetrate the atmosphere, and even hit the ground. To date, scientists have identified more than 40 impact craters that are over 20 kilometers in diameter, and many more smaller than that. Standing on the rim of one of these craters leaves one with no doubt of the awesome potential these objects have to change the face of the Earth. These craters were caused by what would today be identified as near-Earth objects, or NEOs. Generally either rocky asteroids or icy comets, what distinguishes NEOs is that their orbits come close to or cross the orbit of the Earth, which introduces the possibility of an eventual collision. Since the asteroid Eros was first identified as a near-Earth object, there has been an increasing amount of attention paid to NEOs. Engineers and scientists are working on a variety of questions. What are NEOs? How did they come to have orbits that cross Earth's? How can we tell if one might hit our planet? And if we find one that might, is there anything we can do about it? The Space Generation Advisory Council is proud to present this short film highlighting some of the answers to the many questions about near-Earth objects. Given enough time, every NEO is fated to either hit a planet, fall into the sun, or be thrown from the inner solar system. Any of these objects that were formed at the same time as the solar system, some 4.5 billion years ago, would certainly have suffered one of those three fates by now. Yet there are hundreds of thousands of NEOs that have been tracked and cataloged. Since they haven't always been there, there must be some mechanism at work that brings these objects into their current orbit from somewhere else.
NEOs are near-Earth objects, so they're asteroids in orbits that cross the Earth's orbit. They originated in the main belt, so generally they were orbiting the sun in between the orbits of Mars and Jupiter, but they interacted with Jupiter and that changed their orbit, and so now their orbits cross Earth's orbit.
Different physical processes, resonances, or harmonic kind of interactions between the planets can cause them to come into orbits where they enter the inner belt. There is a force called the Yarkovsky effect, which causes orbits to drift a bit because of solar light pressure. And those can cause them to drift into a resonance, so that it's sort of like a pendulum, and as they come into the resonance, they start swinging more widely in their orbit, and then they come in and cross the Earth's orbit.
And if their orbit crosses Earth's orbit, there's a risk that they could collide with the Earth.
These processes take millions of years, so they don't happen. They don't suddenly appear. We have to discover them, of course, but it's not like we have to be constantly vigilant for a new one that gets into a crazy orbit.
So most known NEOs are main belt asteroids that have had their orbits altered by influences from the Sun and the other planets. But what exactly are they? What are they made of?
So O in NEO stands for object. And there are two types of these objects, asteroids and comets.
The asteroids, they basically would be formed of the same materials that form the inner planets. So the rocks would be quite similar to that found in the Earth. Whereas if they come from the outer solar system, i.e. comets, then they'll be mostly icy objects, which most of the icy stuff would have probably melted away by now, so it's just like the remnant dust or whatever's left of it.
And so these asteroids can be like a big chunk of a mountain, just a solid piece of rock, or they can be made of smaller pieces that can be as small as an inch, that are held together by big gravitational force.
But you can't tell that just by looking at them. And astronomical observations, they're just little specks in the sky. They're not even resolved. So for the vast majority of the ones we know about, we have no idea what their structure is. We don't know what their shape is. We don't know that much about them. We only know their orbits.
Whether pebble-sized or mountain-sized, NEOs are tiny compared to the vastness of the solar system. They also reflect very little of the sunlight that strikes them. Finding tiny, dim objects in a very large, dark sky would be difficult at best. Yet there are several professional groups and thousands of amateur astronomers worldwide that are actively hunting NEOs. What do they use to find them?
To look for very small objects, which are very faint, then you have to have a very big telescope. So you can have $100 telescope you can buy in Radio Shack, you can find some. But if you want to find very tiny ones, then you need $1 billion telescope.
One such telescope is the Large Synoptic Survey Telescope, or LSST, which is planned to begin construction in 2010 in Chile. Its 8.4-meter mirror will be able to spot NEOs as small as 100 meters in diameter. But how can a telescope tell you if an NEO is going to hit the Earth?
You take 2 or 3 images during the night spaced out by 40 or 50 minutes, and then you compare those on the computer. So you do a subtraction of the 2 frames and see what moves. And when you see things that move, then you put those together in what's called a tracklet, a little trail of motion, so that you know the position and the rate of motion. That allows you to find it again tomorrow or next week. Once you've done that about 3 different nights, you can calculate an orbit.
How many of the NEOs that have been discovered are actually dangerous?
Not all NEOs are dangerous, because definition of NEO is that their orbit crosses orbit of Earth. But actually, to get collision with Earth, then you have to be at the same time at the same place. And so these are called potentially hazardous asteroids, and they make few percent of all NEOs.
Our current estimate of the population is approximately 1,000 larger than 1 kilometer in diameter. And a 1 kilometer size is large enough to cause global consequences. If such an object were to hit the Earth, it could cause a global catastrophe, a climatic global warming kind of thing, or cooling, which could be extremely hazardous. Now, we have actually found most of those objects, and none of them are going to hit us. As you go to smaller size, then you're dealing with things that can cause a regional disaster, perhaps of the magnitude of the tsunami from Indonesia of some years ago. And there are perhaps 1 million objects that could cause such damage as that.
On June 30th, 1908, an explosion occurred in the skies above the sparsely populated Tunguska River region in Siberia. The force of the blast leveled an estimated 80 million trees over an area the size of Washington, D.C. The generally accepted cause of this event is an NEO on the order of just 10 meters in diameter. What if a similar sized object impacted somewhere else on the planet, maybe in the ocean, or close to or on top of a city?
It's the characteristics of the land. If you hit the land in a city, it generates casualties no matter really how big the object is. If it's 20 kilometres outside of the city, then the mitigation is significant. So you've got this large dependence on displacement for land impacts, whereas in ocean impacts it doesn't really matter as long, in the same area it's going to generate casualties.
Scientists, engineers, space lawyers, and political policy advisors worldwide have come together and created a whole new discipline called planetary defense. Planetary defense is the development and evaluation of technologies that might one day protect us from a major collision with an NEO.
Planetary defense is a very young field, and one of the challenges is to know what's going on throughout the world that relates to this particular topic. So one of the purposes of the conference is to bring the experts together on a periodic basis, as it's going to be every 2 years right now, where we can learn what's going on throughout the world that would affect our ability to mitigate a threat like this if we ever have to.
The 2009 IAA Planetary Defense Conference held in Granada, Spain, allowed experts from around the world to talk about their research and to meet their international counterparts. Stopping or deflecting a massive asteroid hurtling towards Earth will require a monumental feat of technology, and engineers are already designing missions and techniques to mitigate the dangers of hazardous NEOs. These range from a single massive explosive device to fleets of highly specialized spacecraft. But which of these many possible techniques is the most feasible?
The mitigation method really depends on what you're mitigating against. And since we haven't discovered anything yet that's on an impact trajectory, we don't know what we would be mitigating against. So it's impossible to choose, which arrow to choose out of the quiver of possibility. I mean, that would have to be decided once something is discovered.
I'm an engineer, and so if someone were to ask me today and tell me that we've got a particular size object coming in, there are a couple of things I'd have to think about. One is, what if we actually tested? What do we have confidence in that would work now? We have kinetic impact, where we've actually struck a comet before. We know we can do that. So from the engineering perspective, I'm confident we can make that happen again. The second one would be, for example, a nuclear explosive, which we know we could do. There are circumstances where if it's a small object that we would want to design perhaps a number of kinetic impactors that would actually strike on a frequent basis to actually provide enough impulse to move it away. And that would be, I think, an attractive technique. There are uncertainties associated with these things, but in having done it one time, gives you a feel that you can do it again.
The mitigation technique we use depends entirely on how big the object is and how much time we have. But in terms of a developed technology, ballistic impact is really the only thing. So for an asteroid in the sub-kilometer range with a decade or two warning, just run into it with a spacecraft and you can change its orbit enough.
My group at the University of Glasgow did a comparison. And so the two methods we found that were the most efficient were either a nuclear blast from a scientific point of view, or the one that I'm investigating, which is solar sublimation, which quite easily is taking a huge mirror, okay, and you want to focus the sunlight. Exactly if you were a kid and you took a magnifying glass and tried to fry an ant, it's the same idea. We want to focus the light of the sun, which is energy, onto a very small point and burn the material enough that it actually turns directly to gas, or simply then just shoots out the back. This creates enough thrust that actually, over a while, moves the course of the asteroid.
The probability that something's going to be discovered that collides with the Earth is very small. But if something is discovered, that's when you really start putting together your mitigation plan. But it depends on the specifics of the discovery. If it's small, if it's big, what year, how many years do we have, so forth.
One thing to think about on these types of events is that many people think you just send up one rocket. It has to be more than one rocket. You have to send multiple rockets, because if that rocket blows up, you've made a big mistake. So we want to make sure that we get at least one rocket on target.
Another potential method of deflecting NEOs is the use of a gravity tractor. This is a spacecraft that would use only the tiny force of its own gravitational pull to slowly drag an asteroid off of its orbit. Far safer and less controversial than a nuclear blast, this could be an ideal method for moving hazardous objects into safer orbits. It's also something we could do right now. EADS Astrium, a European aerospace engineering company, already has a design for a gravity tractor spacecraft that could be built using today's technology. Now that engineers are designing real spacecraft capable of preventing impacts from average-sized NEOs, questions of responsibility have arisen. Who's responsible for, and who will pay for missions to stop impacts from space?
The responsibility for dealing with an impactor is one of the issues that we hope to begin to discuss more now. I know there's work going on at the United Nations to develop some kind of a protocol for making a decision like that. I think the general view of anybody on the planet would be that a strike anywhere is bad for everyone.
No one is responsible for dealing with asteroid hazard. It's only in the last 20 years that we've even realized there is a hazard, and it's been mostly scientists, people like NASA, who have studied it, but NASA doesn't have the responsibility for defending us. So there is no system. That's why what's so valuable, what the Association of Space Explorers and Rusty Schweikart have done to begin to raise the consciousness through the UN that there might be real important decisions that would have to be made internationally.
At the moment, there really is no one who's responsible for dealing with NEOs in the sense of, if we find one with our address on it, that they're responsible to do something. Not only in the United States, but in fact nowhere in the world is there responsibility to take action to protect the public from the hazards of an impact. If an asteroid with the potential to cause great damage were heading for a third world area where the people there had no capability, I think there would be a certain responsibility, but it has to be responsibility. It has to be a responsible act. You don't want to go out there, say, with a nuclear weapon and blow it up so that all the crumbs then still land in the middle of Africa or something. It may not be helpful. Some entity of government in each country, actually, or at least in the spacefaring nations, has to be assigned the responsibility. Until there's an assignment of responsibility by, in the United States, the Congress and the President, nothing will happen, because you don't get money to do something you're not authorized to do. So authorization or an assignment of responsibility is the first step.
once an agency like NASA or anyone else is assigned the responsibility, then the first thing they have to do is start thinking about it. I mean, right now, the brightest minds in NASA have been thinking about the discovery process, but not about what you do about it if you find one coming at you. And so the first thing that has to happen is a bunch of bright people have to start thinking creatively about how do you address this challenge. Now, can it be done? Absolutely. And a lot of my organization, the B612 Foundation, and others have been thinking about this, but we're not part of the government, and we've been trying to beat on the Congress and the administration and NASA to do the work that, unfortunately, at the moment is being done outside government.
Perhaps the most debated issue in planetary defense is the use of nuclear devices as a prevention technique. They could be used to either vaporize or deflect an incoming NEO, but is the use of such devices justifiable?
At the moment, we do not have a complete inventory of all of the objects that are dangerous. But the very largest of those objects, if we found one coming at us today, would require a nuclear device in order to deflect it.
In certain cases, we don't have a choice. If we get above a certain size, we really don't have a choice but to use a nuclear explosive. And the primary reason is that you can deliver more energy to an object using an explosive device of that type than you can by any other means.
I can't think of any reason we would ever need to use a nuclear weapon. If there is a reason, fine. We have more nuclear weapons than we need right now on Earth, and we might get rid of a few. But that, to me, is a difficult thing to justify because we don't have enough knowledge of what the effect of a nuclear weapon would be.
It's something that we will always need to have around, I believe, because there'll be objects big enough that are so big we don't have a choice but to use them.
It's only the very largest objects that would require a nuclear device to deflect them. And those very largest objects are very, very infrequent compared with the smaller objects, which can use non-nuclear deflection and are much more likely to occur. So we cannot today rule out the possibility that we would have to use nuclear, but it's extremely improbable. The probability is about 98% that if we realize a threat, we could deal with it with a non-nuclear device.
Today, there's a lot of confusion over the potential risks we all face from NEOs. But is public awareness important? Should we be worried?
Public awareness is critical, and we've come very, very far. 10 years ago, we were still talking about a giggle factor, that this was not taken seriously. Now I think it is. But we still don't have a command and control system in place to translate that public awareness into any sort of decision making.
Like any risk, you want people to be educated. You want people to understand the nature of the risk. What should we do about it? How active should we be? It makes sense that the first thing we want to do is characterize the risk, and the best way to do that is observational. Do the surveys, keep track of them.
I don't think anyone should worry about asteroids, but we should be conscious of it, because especially with the larger ones, it is the greatest potential long-term threat we know of. There's nothing else that could wipe out civilization or even humanity that we know about except an asteroid.
No, we don't have to be so concerned, and as time goes on, we can become less and less concerned.
We can sort of begin to put out of our minds the film Deep Impact now. So we put out the film Armageddon, that went ages ago, and now Deep Impact's also on the way, which is good.
Interestingly, it is about comparable to the risk in all but the Middle East of dying in a terrorist act. And so we worry a great deal about that. And so you can't just dismiss it and say, well, nobody worries about getting on a merry-go-round, yet people do die by falling off of them. I can't answer the question, should you worry or shouldn't you worry? It's up to you. But that's about what the risk is. It's in that range.
The more we know about these and know where they are, the less likely we are to get hit by one of them. And so that's a very direct way of affecting how humans are, because if we do get hit by one, that could really substantially change our way of life. And that's something we have an opportunity to do something about now, whereas the dinosaurs did not. We simply don't want to go the way of the dinosaurs.
How can students with an interest in NEO science and planetary defense get involved?
We are organizing the first Future of Planetary Defense Conference in Bucharest, Romania, 2011. It would be basically a one-day conference before the second Planetary Defense Conference at the same venue, and it would be a panel of young experts and few senior experts that would be in charge of the one-day conference. So please get in touch with us and contribute to protecting the Earth.
No human has ever visited a near-Earth asteroid or a comet, but it's possible that we one day will. Let's listen to what the experts think it might be like to stand on one.
I think it'd be less dramatic than we would sort of imagine. Less like the movies, more like a rough collection of rocks. Because in reality, it's probably formed simply by spinning and held together a lot by spinning. So what looks like one solid rock from a distance, when you get close up, in fact, will not be.
It would be like standing on top of a mountain, but instead of seeing distant mountains or sea or wherever you are, you would just see dark space and stars.
If you try to leave a footprint, it'll probably just, either you just like punch straight through, or it depends on how hard you hit the asteroid.
Interestingly, as we go to some very small sized, in the 100-meter size range, some of them are spinning so rapidly that the centrifugal force of the spin, like riding a merry-go-round, is actually stronger than the gravity, and you would literally fly off the surface.
It will be very hard to stand. You have to hold onto something because their gravity is much smaller. If you've seen movies of astronauts on the moon, they can jump very high because gravity on the moon is only 1/6 of gravity on Earth. And it goes with the size of the object. So those people standing on asteroids, they could just do a little kick, even like they're trying to kick a soccer ball, and they could eject themselves off that object. So they have to hold really tight on it.
We don't even talk about a spacecraft landing on NEO. We talk about docking because the gravity is so little. So, it'd be kind of fun, I suppose. You could just float over it.
No spacecraft has yet been sent to an NEO in the name of planetary defense, but several have been sent to conduct scientific studies. As it happens, NEOs can provide us with information about the solar system and possibly even the origins of life.
NEOs are the leftover materials from the solar system. They're the things that the planets were made of. So they're very interesting to scientists.
Looking at the material of near-Earth asteroids, we can learn about what the Earth is either was made of originally, or what, for example, old material in the center of the Earth would still be like today.
One of their theories is that life may have originated on Mars, and which an asteroid then impacted Mars and threw up a load of fragments, which then travelled to Earth in meteorites and then landed on the Earth and infected Earth with life. It could have happened actually the other way around, that life began on the Earth, an asteroid smashed into the Earth, and then transfers life to Mars.
Mining asteroids is currently the realm of science fiction, but is it possible?
If an NEA comes suitably close to the Earth, you can actually nudge it a bit and then actually put it into orbit about the Earth, place it anywhere you want. So I think most people will probably want to put it fairly close to the Earth, but far enough away that it doesn't interfere with any of the satellites orbiting Earth. I think if it's like further away than the Moon, then it would be a bit too difficult to get to.
I think Earth is already overcrowded. We need to move on to other planets. Okay, for now we can talk about Mars, but then, come on, let's be realistic. We're not going to stop at Mars. We're going to go to another planet. Jupiter being a gas giant, we're not going to go there. And moving to any of the Jupiter's moon, I think it's going to be very difficult as well because of the huge magnetic field, very powerful magnetic field of Jupiter. It irradiates anything. You can just go on to the comets, not just asteroids. Go on to the comets, mine them, continue to other solar systems.
Asteroids basically contain all the materials that the Earth contains. So if we run out of a particular kind of metal, we can actually probably find an asteroid containing that kind of metal.
Even if you have just silicates, which may not be that useful right now as we think of, you can actually turn them into structures. You can mold them into different structures. You can use that for setting up another space station.
Since asteroids are made out of the same rocky building blocks as the Earth, Most of the materials that we mine out of the Earth could one day be taken from asteroids instead. These orbital mines could one day make terrestrial mining obsolete and potentially be the first steps in extraterrestrial settlement. With raw materials literally at their feet, hardy asteroid miners could begin construction on permanent outposts upon these tiny worlds. By continuing to advance our knowledge of NEOs and the technology surrounding them, we may one day be able to turn these potential disasters into potential new frontiers. A collision between Earth and a kilometer-sized NEO would cause widespread devastation. But what are the odds of such an event actually occurring in the next millennium or so?
I don't know. I would look it up.
1 in 500. So kilometer guys, they hit every 500,000 years or so.
So the odds, if we were flying blind, if we hadn't already done surveys, our best guess at the odds would be 1 in 300 probability. But we've discovered about 90% of the asteroids, and we're tracking about 90%, and none of them are on impact trajectories.
We have no idea. Yeah. It's small, very small, but...
If it hits, then yes. I mean, it has. The one chance has. I mean, the premise now is that that's what caused the extinction of dinosaurs. And so if that's true, it has hit. And if we look at craters on other planets, it has hit. But 1,000 years for the scale of the universe is really tiny.
I don't know, but it'd be quite interesting if one did.
It can, you never know. It could one could come up tomorrow because there are orbits where they cannot be seen easily.
The odds are small, not zero, but very small, which is a good thing. The ones we're worried about now are the small ones. Things that are 50 meters, 30 meters and higher, maybe up to a kilometer, which are more frequent. So those are the ones that are more of a challenge. They won't destroy our planet or end our civilization, but they could cause serious damage and kill a lot of people. We don't want that to happen.